In order to solve this Faraday's law problem about sliding bottom wedges, first we need to know what is happening here. Okay, in the figure shown here, we can see that there is a magnetic field or magnetic flux, right? But we are going to be focused on this one. But why? Because that area or that surface is inside of a closed loop, right? As you can see here, it's inside of a closed loop. It means that's gonna be represents an area that is changing with time. So the area is changing in time because of this bar is going down with a certain velocity, right? And therefore this area is increasing, right? That's increasing. And from Faraday's law, we know that an increase on the area that is where there is present a magnetic field, the magnetic flux throughout this area will increase, right? Because the area is increasing, then therefore more magnetic flux will pass through. Okay. And from Faraday's law, we also know that the time-changing magnetic flux will induce an EMF, electromotive force, right? And then if there is this area is increasing, that will induce an EMF on this area, okay? And if we have an EMF inside this loop, that will drive the induced current, since it is a closed loop, right? Because we also have a resistor and it is conductor. So the next step is try to solve the first question, okay? In the question A, they are asking us to find the current flow, if it flows from A to B or B to A, okay? In order to answer that, I'm gonna draw here, as you can see, top view figure and a left side view figure, okay? From the magnetic flux equation, where we have that's the integral surface B times dA, right? Product point. That's the equation, right? So then we are going to try to find these vectors inside these figures, okay? Since from the figure shown here, we know that the magnetic field, as you can see here, is going up. It means it's going out of the screen. So therefore, the magnetic field, B field, is going to be equal to plus or positive hat key, right? But we need also to find the dA vector. You also can find this equation as follows: n dot hat dA, right? It is the same, see, right? It's just explained a little bit more with the normal vector that is so important in these problems, because you are gonna see right away, okay? And the first step is to find the normal vector of the dA vector, right? We are going to show that this normal vector is going out of the screen, as same as the B field, as you can see here, right? Let me just show you that you can see here, okay? It's going out of the screen. In this figure, we can also see that we choose that the normal vector is going out of the screen. It means from right hand rule with the thumbs up, out of the screen or up, the other fingers are going counterclockwise, right? And that's called the circulation direction, as you can see here as ds, right? That's the circulation direction. Since the normal vector is going up, the other fingers are going counterclockwise, and that's the circulation direction, right? You have to keep that in mind. Okay, since we already have the B field and the normal unit vector as vectors, I'm going to show you that in the left side view. From the figure here, we know that the magnetic flux is going vertically upward, right? But dA on this surface is going just a little bit up, just, yeah, something like that. I think you get it, okay? So then you can also represent that in hat n as dA, right? As dA. And we can see here that there is an angle between these two vectors, right? And so that's all. Let's find the induced EMF on this loop as this area increases with time because of the time changing magnetic flux. Okay, let's do the math. From Faraday's law, we know that the EMF is equal to minus d magnetic flux time over time dt that is changing with time. Okay, so now I'm gonna draw this like that. The integral surface with the b, and I'm gonna choose this one, okay, where the normal unit vector is going that way. That's a product point. You have to remember that dA. Okay, so we have dt, and b is uniform, so that's constant. It is not changing with time. What is changing in time is this area. This area is changing in time, right? And that will induce the EMF. Okay, so we have b times the area, that's L, times this, that will be something like W. I'm gonna draw it as dW, not ds. That's the another part of this area that is changing in time. So therefore we have that area. Okay, then we have minus d o minus b times L dW over dt, and that's equal to minus b dW over dt is the time, is the distance over time, and that's velocity, right? That's the velocity. So then we have the EMF, the electromotive force induced in this loop is of that magnitude, right? Okay, so now that we have the electromotive force, that is something like voltage, we are going to find the we said that this magnetic flux, that equation, is a product point. We have to use cosine of that angle, and we know from this figure that the angle is theta. So then I was forgetting to put that cosine inside this equation. I'm so sorry for that. Okay, I'm gonna say that's cosine of that angle changing in time, the velocity, but cosine is a constant. Therefore cosine of that angle EMF is minus b times L times b times cosine of the angle between the two vectors dA and b field, the b vector, or also the normal unit vector times the b field. That's the same. Okay, so that's the induced current. Okay, now let's focus on this sign that is negative. From Lenz's law, we know that is going in the other direction to oppose that magnetic field or magnetic flux increase. So as we said here, the magnetic flux throughout this area is increasing. From Lenz's law, we know that will induce a current to oppose that magnetic flux increasing. So in order to do that, we had to make a current in the opposite direction to create a magnetic field, and oppose that increase. Now let's focus on the direction, right? So as we chose that the normal unit vector is going up, right? Is going up. We, by the right hand rule with the thumb, represents the normal unit vector, and the other finger represents the direction, the circulation direction. There we have that the circulation direction is going in this way. So that's the circulation direction, right? As I represented here. Thumbs up, and the other fingers represents the circulation direction. Okay, that's the right hand rule. Okay, so this negative sign means that is going in the other way, that is going the circulation direction, opposites. Okay, so then the induced current will flow in that way by the right hand rule. That's what it means, this negative. If you can also do the right hand rule with that induced current, you can see this induced current will create a magnetic field going into the screen. So then we are going to have a magnetic field going into the screen, opposing that increase of the magnetic flux throughout this area. So be careful with that. So as we already found that direction, negative opposite direction of the circulation direction, so that therefore the induced current is clockwise. Okay, it is clockwise direction. And also you can also represent it here, and you can say that current is going in that way, induced, and that means that this current will flow through from B to A. So then you can answer the question. Okay, so that's the first question. We already answered. Okay, now let's focus on the B question that is asking us to find the terminal speed Bt, B sub t of the bar. Terminal speed means that is a constant speed, right? That will never change. So it means that when the loops moves, this loop going down with a velocity, going down at a constant velocity, the so-called terminal velocity, the forces acting on these loops then will be zero, since the gravitational force that is acting on this bar and the magnetic force that we are gonna see in a little while are equal but in the opposite direction. It means that there's not gonna be an acceleration by the gravitational force, right? So let's do it. As we already did free body diagram here, where you can see the forces acting on that bar, we are gonna say, as I told you, the terminal velocity is a constant velocity, because since at rest, when this bar is released, it is accelerating, right? Because of the gravitational force, right? Just give me a moment. Now I'm gonna be focused on this another force, the magnetic force. As you recall, the magnetic force is equal to I, current, L, and B. That is a cross product. It means that there is a sign inside that. Okay, now just let's do it, this equation, let's solve it. The magnetic force I, current, times B, sine of what? L is going that way, L, and B is going in that way. So there will be 90 degrees. So that will be equal to 1. So as I, that is the induced current, induced L times B. So that's the magnetic force. As you can see, we need to use the right-hand rule. Current direction, direction of magnetic force. If you do that, magnetic field direction, that is going out, then we are going to have the direction of the magnetic force acting. If you did the right-hand rule in the correct way, then you are going to have the magnetic force going in that way. And here you can also see the gravitational force acting on that bar. From the left side view, we can see that this magnetic magnetic force is going in this way. In gravity is going in that way. As you recall from physics 1, mg times sin theta represents the magnetic force, the gravitational force acting on that bar that is accelerating this bar down. Okay, but the magnetic force is going in that way, so then I'm gonna multiply that by cosine of that angle theta, and that will represent the magnetic force acting on that bar that is going up. Okay, so the terminal speed means that the sum of forces is equal to 0. Then there will be no acceleration, so the velocity is constant. Let's replace the current induced, as we found right here, in minus B L B cosine that angle theta over R. That's the current induced. Okay, times L times B. But as I told you, I need to multiply that magnetic force by cosine in order to get that direction of the magnetic force. Okay, so I'm going to write cosine of theta will represent the magnetic force acting on that bar, since there is no friction on these rails. Okay, then we are going to have is minus B L B squared B squared L squared B cosine square of theta over R. Once we have that, the conservation of energy, we have that the sum of forces must be equal to 0. So the forces acted on that bar is the minus F, the magnetic force, plus the gravitational force must be equal to 0. Let's replace that into that equation, but okay, minus B squared L squared, terminal velocity, it is BT, constant velocity. Since there is no acceleration, the velocity is constant, then the forces are equal. Okay, cosine square of that angle over R equal to okay, this sign minus positive 1, therefore gravitational force is mg mass gravity sine of theta. Okay, so let's find the equation for BT. R mg trigonometry, basically B squared L squared Okay, sine theta over cosine square of theta. Simplifying, we have that terminal speed are mg b squared l squared, that will be equal to tangent theta over cosine, right? And that's the equation that represents at terminal velocity. Constant velocity where the magnetic force is equal to the gravitational force. Therefore, there is no acceleration occurring. That's so important. Okay, so that's the terminal speed. Now let's focus on the C question. Okay, in the C question they are asking us to find the induced current, but we already did that. So here there is the induced current. Copy. Okay, so there is the induced current. So we already did. That's the magnitude of the induced current that is going clockwise direction. I already replaced the induced current here, as you can see. Okay, in the D question, they are asking us to find the rate at which electrical energy has been dissipated throughout the resistor. Okay, from the electrical power, we know that power is equal to induced current times the EMF. Okay, that equation represents the rate at which an electrical energy has been dissipated throughout the resistor. Okay, so I'm gonna try to current induced is EMF, therefore it will be squared EMF over R. That's the same. I already replaced the EMF that we found before over R. So then we have that is B squared, U squared, B squared, cosine squared of theta. I already replaced the terminal speed that we found before, and that's the magnitude. Okay, so I'm gonna simplify that. I'm gonna say it, power is equal to B squared R, our resistance, mass squared, gravity squared, over B to 4 tangent squared over cosine squared. Okay, from the EMF, okay, this EMF that has a cosine inside, and that's cosine squared. Then I'm gonna say that these two cancel, and the power is equal to mass squared, gravity squared, over V field squared, L squared times tangent squared, and that's in joules times second. That's the rate at which electrical energy has been dissipated throughout the resistor. Okay, therefore, according to the conservation of energy, that's the energy that we are losing throughout the resistor, probably through as heat, right? So that will be called joules heating the energy is being dissipated. Okay, and therefore we need to input the same amount of energy. So let's find it. In order to find it, we have to answer the next question. Okay, in the equation, and final equation, they are asking us to find the rate of work, that is joules over second. It means rate of work done by gravity on the bar. Okay, so let's find it. We are going to establish that the rate of work is driven by this equation. Okay, dW, that's the delta work, over dt, that's joules over second, that's power. Okay, as same as we did before. Okay, now since that is power, so that's gravity force times the velocity, the terminal velocity. Why terminal velocity? Since the gravity force are newtons, then we have to multiply by the distance, by m meters, time s, right? Times s, in order to find watts of the power. So BT is equal to gravity force, the gravitational force, or a distance that we define dW over dt, and that's watts, right? Okay, so now we are going to replace the terminal velocity as we did before. I already replaced the terminal velocity here that we found before. Now we're going to replace the gravitational force that is driven by mass times gravity times the sin of theta times the terminal velocity, the terminal speed, and L tangent cosine of theta, and that will give us to R m squared g squared b squared L squared theta over sine cosine times cosine of theta, and that will give us that the rate of work done by the gravitational force is driven by this equation. Tangent square. And now we find it. That's the rate of work done by the gravitational force, right? That's the input of energy. The energy that is being dissipated over time throughout the resistor is the same amount. That is according to the conservation of energy, right? I'm gonna paste right side, and that's all. That's the same. It's the amount of energy has been paid through the resistor. And check the both are the same, so that's according to conservation of energy. That's physics. So thank you for watching. Thumbs up and subscribe. See you in the next video.